So welcome back, everybody, to EE240. It's February 2nd. In order for it to have a reasonable idea as to what those parasitic really are. So indeed, the way we'll capture that is with these so-called AS, AD, PS, PD parameters. And each of these really just stand for an either area or perimeter. So as you might expect, AS and AD, those are both the area. Those are both areas of either AS is the source, AD is the drain. And similarly, PS and PD, those are essentially the perimeters of those drain or source areas. Now, one thing that I will note that you have to be a little bit careful about is that specifically with these perimeters, you actually should not count this internal gate edge here. Okay, so in other words, PS and PD both only count, and let me do it in a slightly different color so it's clear. They both are only counting basically these parts like this. Okay, so it's only the outside edges that count when you actually put that into SPICE. By the way, anybody know why that is? Why is it that SPICE is sort of set up that way? Why is it that you might not explicitly put that inner gate edge into your instantiation of the model? Yeah, so what you said is it's already captured in the model. And by the way, the reason why it's basically already captured is because that particular side of it has to be there. Right? There's no way you could draw a transistor that would not have that inner edge in it. Everything else, there may be some other rules or something you can play around with, but that inner edge basically has to exist. So at least in 90x% of the models that I've seen, that's always actually captured inside of the model in any case. Okay? Yeah?
Why is the overlap cap on the NMOS a lot smaller than PMOS? Or like the descriptive value for reference?
Oh, so you were asking about the overlap cap between NMOS and PMOS. Is this from the previous slide, or? Oh, okay. So you're asking why is the overlap cap from the NMOS different than the overlap cap from the PMOS? I don't know why it was set up this particular way on this model. It may happen to be just sort of, something that they assumed about what the actual overlap between the gate and the source drain edge. And that may be different between NMOS versus PMOS. But as I said, don't pay too close of an attention to these numbers here, because they're really not necessarily related to anything real, and certainly not to the particular model that we're playing with. Okay, so if we come back to sort of this picture here, again, the real critical point is that if you don't know sort of how the model is set up, or if somebody has nicely enough taken into account it for you, you definitely have to add these AS, AD, PS, PD parameters anytime you're trying to instantiate a transistor and get a reasonable estimate of its real performance. Okay? And so maybe the most practical way to sort of highlight that is that if you go and you do your project and you have these amazing specifications, and I go and I just open up your SPICE deck and I see that there's nothing there, I'll beat you up. Okay? Because clearly it's just wrong, right? So keep that in mind, user beware. Now, the other thing that I think many of you have sort of seen before is that if you start really building big transistors, meaning very wide widths, you tend not necessarily to actually want to just keep on increasing this dimension here. And in fact, it turns out that if you're actually clever, you can oftentimes improve the performance of your circuit simply by sort of playing a simple geometric trick. Okay? So the geometric trick I'm going to play here, I'm going to try and sort of draw, kind of initially just show sort of conceptually how you would get there, and then the picture underneath it really shows what happens. So let's say I take this transistor that I'm building, and I basically split it into two pieces. Okay? And then what I do is I take sort of, as an example, this left half of the transistor, and I kind of just fold it over like this. Okay? So I literally just take that thing and essentially do this. Okay? If you kind of think about it, that ends you up with a picture that I'm showing you here. Okay? Now, the reason that this is actually an interesting thing to do is that notice if I look at this terminal right here, which in most cases, by the way, you'll choose to be the drain of the transistor, notice that I've actually cut the total area of that junction there by a factor of 2. Right? Because essentially for the same total transistor width, right, I've got these two transistors now in parallel, or each of them had half of the width of the original transistor. So in other words, I've got, sort of current from this device as well as current from that device. I only have half of the drain junction area that I had in this particular configuration. Okay? Now notice, of course, on the source, I still had the same area as I have before. But you can imagine I can keep kind of playing this trick and folding more and more times and sort of get it so that it's slightly more even between the source and the drain. Okay? Does this make sense to everybody? Or? So just a couple of maybe, let's say, related questions or points here. So the first is that I would actually argue that for reasons that we talked about, maybe about a week and a half, 2 weeks ago, I tend to build all of my transistors out of a unit cell that actually looks like this and not like that. Anybody have, why might I do that? What's the advantage of doing things that way? Yeah.
So your current flows both up and down.
Yeah, exactly. So you said exactly the reason we talked about, which is notice my current always flows both up and down, right? In other words, if this is my unit cell, as long as I don't rotate it by 90 degrees relative to something else I'm trying to match it to, then I'm basically guaranteed that I won't screw up in terms of my current flow directions with matching multiple different devices. Now, by the way, it turns out the other, let's say, reason which we just talked about why you want to do this is that indeed, if you do things this way, at least on one of the two junctions, you'll have a lower parasitic cap than you otherwise would have had because of this sort of geometric sharing effect that you get. Does this make sense to everybody? Or? Okay, now, the other thing I just want to briefly mention, because for better or for worse, you'll probably run into this particular issue, is that there's a lot of, let's say, I shouldn't say debate, but there's a lot of confusion that arises around essentially the fact that oftentimes you lay transistors out this way. And in particular, if you're trying to sort of simulate things or even draw them in cadence, you'll usually see one of two parameters that you can specify. One of them is a so-called M factor, and the other one is usually called NF, or number of fingers. Okay? So, by the way, how many of you guys have ever actually sort of seen this in a cadence installation before? Okay, great. So, maybe we'll actually do this as a poll. Who thinks they actually understand what the difference between NF and M really is? Okay, what do you guys think it is?
M is just that if you increase, you just get multiple copies of the same thing, and with NF you increase the number of figures. So you get, you add more gauge to the structure you already have.
Okay, great. So you actually said what it really should be defined as, which is indeed in SPICE, if you say M equals, let's say, 2 as an example, what it will literally do is whatever you specified for the original transistor, it'll literally take another complete copy of that transistor and tie the two of them in parallel. Okay, in other words, everything, all of the terminals will just be tied in parallel with each other. Okay? In SPICE, at least, that's the only correct, quote-unquote, definition for M. Okay? Whereas this so-called NF, that typically means that you're taking some transistor, and I'll just sort of explain how that's typically used. If I had a transistor that, for example, had a W of 2 microns, but an NF of 2, what that typically means is you'd end up with a layout that kind of looks like this, where each of those widths there is actually 1 micron. Okay? Now, again, unfortunately, because there tends to be a lot of confusion around this point, it's not always entirely clear. You know, somebody may say NF of 2 versus, width of 2 and things like that. Basically, make sure, if somebody sort of gives you a schematic or just comes to you and, draws or gives you an instantiation or something, have them sit down and draw what they actually intended to have this model. So ask them, did you really mean something where there's like literally 2 transistors in parallel? Or did you mean something where, there's some junction sharing going on or something like this? Okay, and in fact, even from a real SPICE model standpoint, if you literally had 2 transistors with some space in between them versus 2 transistors with a shared junction, those 2 are different. Okay, so just make sure when you're communicating with people that it's very clear what you're both actually talking about the exact same thing. Okay? Yes.
Well, not like that. Like normally you would connect them anyways, right? I mean, I understand the difference, but like in terms of what would it actually look like, would normally want to communicate like that?
Oh, okay, so the question was, if you're really laying this out, I guess, are they really different? Or in other words, would you really ever do something that looks like this, right? And so the answer is it really depends, okay? Because, for example, if I have, let's say, a big enough transistor, I might not do it all in one row, or one column for that matter. I might actually have 2 columns, right? And as an example, that would be something that would probably have, I would kind of instantiate that as a transistor, as one transistor with a certain number of fingers and a certain total width, and an M of 2, just as an example. Right? Similarly, by the way, there may be times where, from whatever reason, you really can't afford to have 2 fingers like this. So as an example, you need the absolute smallest transistor you can possibly build, but you still want it to somehow match. Right? Well, if you're going to do that, then what you'd have to do is you'd have to take 2 of these things like this, and you probably would need the diffusion break just because you have to have separate connections for the sources and drains for each of them. Right? And then indeed, you'd again want to instantiate something that was literally an M equals 2 rather than implying some sort of drain junction sharing. It's a good question. Yes?
So when you do M equals to 2, does it also capture the spacing between the 2 transistors?
Not necessarily. So again, and this depends on, you have to be a little bit careful between, let's say, what you put into cadence and what actually pops out in the model, which is why, by the way, I'm never a big fan of GUIs. I actually like to look at, in text what's really happening. But basically, in SPICE, for example, if you were to take this instantiation here and just say M equals 2, it doesn't know anything about the space. It literally just takes the exact same model and puts another copy of it directly in parallel. So it won't model anything about extra wiring or anything like that. It will just literally take it and put another copy of that device in parallel. It's a good question. Okay, any other questions? Okay, so just one other sort of note on this before we move on. It turns out that because obviously this question of junction sharing versus not pops up quite a bit, there are some things in SPICE that were sort of added in at some point to try and make things a little bit easier for you to specify that. So for example, if your model has a so-called ACM equal to 3, and I'm not actually sure what ACM stands for. I think it's like automatic capacitance modeling or something like that. But basically, if this is set to 3, then what happens is that SPICE tries to sort of intelligently figure out what the layout actually looks like without you explicitly saying what AS, AD, and etc. actually are. Now, there's an additional parameter you need to add into the model in order for it to actually have something to calculate these numbers on. That's the so-called HDiff. So this is half of the heavily doped minimum diffusion length. In other words, if you looked at these pictures, there's always some like minimum kind of width or length with that diffusion. Right? So that HDiff is just telling you what kind of is half of that dimension so that SPICE can go and actually calculate, effectively what AS, AD, and etc. would be based upon knowledge of that HDiff. Okay? So again, you actually will not get to use this in this particular model because I didn't turn it on because I want you to actually explicitly, be careful about AS, AD, and etc. But you will potentially see models that have this, which is why I wanted to just sort of briefly mention it here. So in models that actually do have this ACM equals 3, the sort of terminology or the additional parameter that you would use to kind of control that is the so-called GEO parameter, which obviously just stands for geometry. So if you say GEO equals 0, that means there's no sharing of any junctions whatsoever in that transistor. If you say GEO equals 1, the drain side is shared, but only the drain side. If you say GEO equals 2, only the source side is shared. And if you say GO equals 3, that means both sides are shared. Okay, and both sides are shared obviously means you probably have some many fingered, multiply sort of folded transistor. Yes?
Shared with what?
So what it means, it could mean shared with another transistor, or it could mean sort of shared with itself in this same sense that we've kind of been drawing here, meaning where I took one physical transistor and just kind of cut it up into smaller pieces, and I kept playing this folding game that we talked about. Is that clear? Or maybe just the video, the question was shared with what? Is that clear?
Well, so I guess it's kind of an approximation. I mean, say if you have like something with 3 fingers, then none of these options are correct.
Okay. So the question was, let's say that you had something with like 3 fingers, then technically none of these options are really correct. So in other words, is this really just an approximation? And the answer is absolutely yes, right? So typically you would do this before you even had any of the layout, and you just sort of enter these parameters again to try and get a rough guess as to what things actually look like. Of course, once you have the real layout, the real number should be entered into the model so that it gets that correct. Now, by the way, for that reason, that's also why I didn't turn it on in our particular model, because I want you guys to think a little bit about what are the real sort of areas and perimeters of whatever sort of topology you would really be using. Is that clear? Okay, great. So unless there's more questions on that, let's actually go ahead and kind of move forward and really start talking about something that I think most of you are already familiar with, which is essentially, we spent a lot of time just talking about what the capacitors are, but at the end of the day, it is typically easier to think about sort of a figure of merit. And it turns out that especially for most of the designs that we will be doing, the figure of merit that you're going to care most about is the so-called unity current gain bandwidth, or omega t, or similarly ft, and the two are just, of course, related by a factor of 2 pi. Okay? So I'm again assuming that all of you guys have seen omega t or ft many times before. As you should hopefully know, it's really just defined or really set by GM over CGS plus CGD. Okay? And again, the real reason why this turns out to be pretty useful is that if you know what your omega t is, that gives you a really good hint as to sort of how hard are you pushing on the transistors relative to the sort of circuit bandwidth or circuit characteristics you're interested in the first place. And a little bit later on, I'll actually show you more explicitly how we can directly even use this omega t to basically calculate kind of power consumption and things like that in the amplifiers that we're interested in. Okay? Again, I'm assuming everyone has seen omega t at least, 3, 4, 5, 6, whatever times, so that I'm not going to spend a lot of time on it. I did want to mention just a couple of brief things, though, which is obviously we could take just as a simple example, our long channel transistor model, and you could pretty much directly calculate it just based on the definitions of GM and sort of what the total CGS and CGD would be set by. Essentially what the omega t should be as a function of a few fairly simple parameters, right? So obviously the mobility comes into the picture. In this case, I've written it as overdrive, but you could actually replace that directly with V star since it's the same in the long channel device. And you can see that there's this L squared on the bottom here. In other words, if you reduce the channel length, let's say by a factor of 2, your omega t should actually go up by a factor of 4 for the same V star. So just to make sure it's clear, why is it that happens? What are sort of the parameters that are changing that cause you to get an L squared behavior? Yeah, okay, so you just said the GM is basically proportional to 1 over the length, right? And the capacitance is proportional to the length. So in other words, if you decrease the length, the GM goes up and the capacitance goes down, right? So you get an L squared. Okay, so now just to be totally clear, if we were to take an extremely short channel device, and by this I mean something that's completely velocity saturated, I've already shown you here that I now claim that the omega t would only go linearly with the channel length. So why is that? Which, out of the two terms that we said above were both changing with length, which one of them is no longer changing with length? What you have a completely velocity saturated device? Yeah, GM, right? Because basically the only reason GM was changing with length was that effectively the velocity of the carriers was going up. If you're not completely velocity saturated, sorry, not going to help you any. So it's really only from the capacitance now. This kind of has an interesting physical interpretation in the sense that this is kind of telling you that your maximum frequency is sort of related to how fast the carrier can get from the drain to the source, right? And that's just set, obviously, by the channel length there. But indeed, that's why you sort of get this regime where, much like with the drain current, the omega t will be somewhere between linear and quadratic on the channel length. Does this make sense to everybody? Or? OK, so, oh, yes.
What exactly is omega naught in this context?
Oh, yeah. So the question was, what is this omega naught? Omega naught was really just, oh, I don't know why it keeps changing to white. OK, so omega naught in this context was basically just this whole quantity, just kind of by definition. There's nothing particularly magic there. It's just I just define omega naught as being this mu v star over L squared. That's all.
Well, I mean, can we kind of think of it as the frequency we can operate at safely in order to get...
I mean, to the extent that it's related to omega t, and again, we'll say some more about this a little bit later on, but basically omega t really tells you, if you looked at that omega t relative to kind of the gain bandwidth of your circuit, it basically tells you sort of how much are the parasitics from your own transistor going to really impact essentially how much power you have to dissipate and really whether or not you can even hit that bandwidth in the first place. So clearly, if you're operating at something like beyond omega t, for most of the circuits we're talking about, it's just not even actually possible, right? And again, as we'll actually show a little bit later on, just once we've sort of worked out all of the different kind of pieces of the model, it'll turn out that basically, though, as you get closer and closer to that omega t in terms of the gain bandwidth, you'll have an effect where basically the power will just start shooting up very, very quickly. Okay, so we'll actually talk about that a little bit more in 1 second. But again, the exact details of that I'll derive in a few more lectures. Okay, it's a good question. Okay, so as we've kind of been hinting at throughout this whole process of this lecture, what we can always, of course, do is look at how do we trade off between essentially our current efficiency, or our GM over ID, which of course means that we'd be tweaking our V star, versus that omega t, right? And I apologize, the colors here are not great, so let me actually maybe try and fill in sort of on top of this curve here. But basically what you can kind of see is that, and then as you should hopefully also very much expect, is that as you increase, in this case, the VGS minus VT, but that's really equivalent to just increasing the V star, right? Your FT or your omega t will get better, but your GM over ID will get worse, right? So in other words, there's always this trade-off between basically sort of how fast you can make the transistors intrinsically versus the current efficiency you can actually get out of them, okay? So as you might expect, I'll actually come back to this one in 1 second, but this just says that if you scale the devices, the FT gets better. As you might expect, we're engineers, we're kind of lazy. So anytime we get sort of two things that are trading off with each other, you'll typically just sort of try and come up with some composite metric that tells you, roughly speaking, what's kind of like the best of both worlds, right? Like, in other words, how do you get both a reasonable speed out of the device and a reasonable current efficiency? Okay, so that's where this so-called FT times GM over ID metric would come from. And it's just saying, if I had an ideal device, I would want this metric to essentially be infinite, right? And if I don't, then I can kind of look at what are the regions where this composite metric comes back and gives me something, that looks reasonably good in terms of balancing those two things out. Okay? So what you can kind of see here, and which is hopefully not too surprising, is that especially as you go to these more modern technologies, and by the way, notice I've stopped the curve here at 0.18 micron. You guys are using a 90 nanometer model, so you can imagine sort of what the curve does there. Basically, the sort of peak composite figure of merit tends to be at relatively low VGS minus VT. Okay? So you can see here, and by the way, that implies that it's also at a relatively low V star. So as an example here, you can see the peak is somewhere between, about 100 to 200 millivolts VGS minus VT. And indeed, it seems like it's kind of moving perhaps downwards as you sort of scale the technologies further. But basically, this is now sort of how I'm going to finally motivate why it is that I kept choosing a V star of about 200 millivolts. Okay? The reason I kept choosing that was not because that I necessarily knew by default this was always the best possible thing to use in a particular circuit. It was simply that I know that this always, or not always, but at least for the types of transistors we're dealing with, typically gives me a very reasonable trade-off between that current efficiency and the actual transistor performance we can get. Okay? Does this kind of make sense to people? Or? So let me maybe sort of ask a couple of related questions maybe. So let's say that from whatever reason, you're dealing with, let's say, some standard that says, okay, I always have a certain bandwidth that I have to be dealing with. Okay, this could be like a radio baseband or some chip-to-chip communication or something like this. So if I go and I scale my technology, and I want to sort of get the best possible power efficiency for that given standard with that given bandwidth, what do you think will tend to happen to the V star that you will choose? Yeah, you're going to tend to choose it lower. Why? Yeah, okay. So you said you get better efficiency there. And why is that kind of okay if I'm scaling from one technology to the next? Why can I afford to actually get that better current efficiency? Yeah, okay. So you said you're trading off FT for it, right? So to the extent that scaling the technology actually gives me a faster transistor, I will tend to push that V star down so that I can actually exploit the fact my transistor got faster and basically bring me back to the original bandwidth I wanted in the first place, but just get better current efficiency out of it, right? Similarly, let's say that you know you're building just the absolute fastest thing you can possibly do in the technology, right? If that's the case, this 200 millivolt number that I kept using may or may not be the right number, right? Because typically what tends to happen, and again, we'll sort of derive this in a little bit more detail later on down the road, if I do a sort of plot of my power consumption versus V star for some given, essentially, bandwidth that I need to achieve, what you'll tend to see is a curve that looks sort of like this. Okay? Now, by the way, can anybody sort of tell me why the curve looks this way? And in particular, as an example, let's just start with the easy side. Why do I get sort of power increasing, in this particular case, linearly as I increase my V star too much? Why is that? Yeah, exactly. Remember, V star just tells you directly of the relationship between GM and ID. And if you increase V star, you're decreasing the GM you get per unit ID, right? So that means that if I have a fixed capacitive load I'm driving, then as I increase my V star, I just need linearly more bias current to drive that capacitive load. Okay? So now, what's happening on that side of the curve? Why is that side of the curve starting to come back up? This is the slightly trickier one, by the way. So you have, say that again? Higher frequency. So what do you mean by higher frequency? Okay. So by the way, when I'm moving in this direction, as you decrease the V star, what happens to the FT of the device? Does it go up or does it go down? It goes down, right? So as the FT of your device goes down, and now let's maybe just draw, I'll just draw a picture maybe over here since I have a little bit more space. I'm just going to draw sort of the simplest transistor amplifier. I'm not even going to draw the bias current source because I'm lazy and I don't have enough space on the top of the slide here. So let's just pretend I have a simple common source amplifier, and I've got some explicit fixed load capacitance I have to drive. Now, as you decrease that V star, what are you sort of doing from a sizing standpoint to the transistor? Is the transistor getting bigger or smaller? Yeah, it's getting bigger, right? If the transistor is getting bigger, what does that mean about its parasitics? And in particular, let's think about just the drain to body parasitic. Does that decrease the V star? Is that parasitic getting bigger or smaller? Yeah, it's also getting bigger, right? Well, if you get to the point where this parasitic is comparable in size to the cap you're driving in the first place, what's going to happen is you're going to start spending more power to drive your own parasitic, right? You won't quite get the bandwidth you want, which means you have to spend even more power, and you'll have even more parasitic, and so on and so forth, right? So in other words, at some point, as you get very, very close to trying to actually have the transistor give you a gain bandwidth, which is kind of equivalent to the gain bandwidth it can even support intrinsically from its own parasitics, that's when you start having this basically explosion in power consumption over here. Because again, what happens is, and again, I think you actually probably talked about this in, for example, 141, this is a so-called self-loaded limit. Right? It's basically saying, as you keep decreasing that V star, your FT is going down, and then if that FT gets close to the gain bandwidth you were trying to hit in the first place, you can spend as much power as you possibly want. You just won't be able to get that speed. Right? Because no matter how much power you're spending, the transistor driving itself just can't possibly hit that speed. Okay? So by the way, it turns out that, over a pretty reasonably wide range of the gain bandwidths that you're probably interested in, this curve here is typically centered at approximately 200 millivolts V star. Okay? So that's kind of my admittedly very hand-wavy, but turns out to be quite useful reason for choosing V star of 200 millivolts all the time. So in other words, that's kind of what I was applying here on the slide. If you're not sure what to do with V star, start with 200 millivolts. It's usually a pretty good guess. Okay? And then you can kind of move it around a little bit, and you'll get a pretty good idea as to, well, okay, should I really be much lower, much higher? But, if in doubt, just start with 200 millivolts. That's probably a pretty reasonable guess to use. Does this make sense to everybody? Or? Okay, great. So I just kind of summarized here at the end. If you remember, we had talked about kind of what the small signal design procedure we were using was. I've just kind of summarized this here, mostly just kind of as a reminder. I'm not going to walk through it again because I think really the best way for you guys to learn how to use this is to actually use it. And so don't worry, you'll be doing that. That's what the next homework is actually for. But this is just sort of maybe a brief kind of summary thing so that you can kind of come back and look at the slide and remind yourself what the procedure we talked about actually is. So, any last questions on this before we move on, or? Okay, if not, we're actually going to sort of somewhat or largely speaking change topics now. And the next topic we're actually going to spend probably the next 2 to 3 lectures or so on is essentially the issue of noise in electronic circuits. Okay? Now, you may be wondering, why are we going to spend time talking about noise? And the reason is actually quite simple. Okay? It turns out that especially in sort of the analog circuits that we're going to be talking about, or rather, if you're even going to be dealing with analog circuits in the first place, in many domains, the sort of fundamental noise you have in electronics sets the minimum power consumption that you actually have to dissipate in order to get your circuit to work. Okay? So in other words, if you say this another way, you actually have to understand noise very, very well to actually be able to do low power circuit design, and again, many of the contexts that we're going to be interested in. Okay? So just maybe as kind of a reminder, and in fact we'll derive many of these things as we go through, the reason that this really happens is because it turns out that the way sort of noise impacts our analog circuits is that it forces us to increase power very, very quickly as we try and improve our so-called signal-to-noise ratio, or really another way of saying improving the precision. Okay? And the reason for that is fairly straightforward. So let's say we're just thinking about some very simple amplifier, right? Well, the maximum signal power I can sort of get out of that amplifier is usually tied to the power supply, right? And the reason for that is very simple. The larger the power supply is, the bigger the voltage swing I can get out of that amplifier, right? And that kind of says what the biggest signal power I can actually get is. Well, as we'll see actually very shortly, maybe not this lecture, but certainly by next lecture, the sort of total noise you have at the output of that amplifier is almost always set by kBT divided by C, where kB is just the Boltzmann's constant, T is the temperature of your circuit, and C is the capacitance, the total capacitance at the output of your circuit. Okay? Now, one thing that I'll already point out is that notice there's not really much you can change in that expression, right? Boltzmann's constant, well, if you figure out how to change that, again, let me know. You're going to have some Nobel Prizes. I want some of the prize money or something like that. Temperature, well, okay, maybe you could do something, but generally you can only move that the wrong way, because unless you have a cooler on your chip, you can only kind of heat things up, and again, that makes things worse. So the only thing you can really do is control the capacitance, right? So as I actually sort of already noted here, that means that if you want to get lower noise, that means you have to increase your capacitance. Okay? And of course, as we saw before, the current you had to spend in your amplifier was directly related to the capacitance, right? Because the higher the capacitance, the more current you needed to support a certain gain bandwidth. Okay? Now, as we'll spend actually a lot of time talking about in 1 second, this signal-to-noise ratio is really specified in the so-called, let's say, variance, meaning that we're not dealing with, let's say, a voltage over voltage. You're actually dealing with essentially a voltage squared over a voltage squared. Okay? So that means that, for example, if you want to improve your voltage precision by a factor of 2, you actually have to make the capacitance 4 times larger. Okay? That implies that the power consumption you have to spend also needs to be 4 times larger. Okay? So if somebody comes to you and says, okay, I want my amplifier to have twice as much precision as it had before, or even 4 times as much precision as it had before, you should, sort of look at them, well, really, that's not really that easy. Okay? Because that actually very, very quickly adds up, right? If they tell you they want 4x the precision, that's 16x the power if you're really limited by thermal noise. Okay? By the way, this is one of the biggest contrasts that you'll see between analog circuits and digital circuits. Because just to be clear, in a digital circuit, if you wanted to, let's say, double or quadruple your precision, what would you have to do? Yeah, you add bits. So if I wanted to double precision, how many bits do I add? I add 1 bit. If I want to quadruple my precision, what do? I add 2 bits, right? Well, that doesn't, big deal, right? I went from 10 bits to 12 bits, or 14 bits to 15 bits, or whatever, even 31 to 32, right? Big deal. Doesn't really change much, right? Well, in the analog domain, not so easy, okay? Because every single bit, indeed, actually costs you quite a bit, quite a large amount of power. Excuse me. Okay. In fact, actually, I think I'll have this example a little bit later on, but I would encourage you guys to even calculate in the analog domain. If you wanted to, for example, get 32 bits of resolution from an analog amplifier, which, by the way, I don't think anybody has ever actually really done, but let's just pretend. Calculate how big of a capacitor you would need, given that your power supply voltage is only 1 volt. Okay? And you'll see that the number you'll get will be something astronomical, and which is why, obviously, no one has ever really actually done it. Okay? Okay, so before I sort of dive too much further into talking about noise, I do have to make one point very clear, which is, and by the way, I'm guilty of this particular sin as well. Many times when people talk about quote-unquote noise, what they really mean is junk that they did not want. Okay? In other words, anything other than the signal they were actually interested in. Now, the thing we have to be very careful about here is that technically, that's not really, not all possible things that you don't want are actually noise. Okay? So when we talk about noise here, we really mean basically fundamental noise essentially caused by the devices themselves and caused really by sort of the discreteness of charge. I'll say some more about that in 1 second. But to be really maybe totally clear, what I actually mean by this is that if you actually have something that's noise, if somebody goes and asks you the question, what will be the value of the noise at a certain time, your answer should be, I don't know, and nobody does. Okay? Because it's truly random. Right? It cannot be predicted. You can't say anything about the actual value. You can only say something about the statistical properties. Whereas, for example, if you talk about something like quote-unquote supply noise, well, hey, in principle, if you knew what all of the different transistors on your chip were doing and you knew what the current waveforms that they were drawing from the supply was, you could immediately calculate what the variation in the supply voltage should be. Right? Similarly, if you had one gate next to your analog circuit and that gate happened to be flipping its output, again, you should actually know what the voltage signal in time would be due to that. Okay? So in other words, what I'm getting at here is that when we talk about noise here in this class, we're really going to be focusing on the true random fundamental things that you cannot actually control. Whereas everything else, even though, believe me, it's probably just as annoying, if not even more, you should really be, if you're trying to be careful about it, you should refer to that as interference and not as noise. Okay? Is this clear to everybody? Or? Okay, so again, for today, we're really going to be focusing down here on the so-called fundamental noise sources. So just to be sort of totally clear here, and hopefully some of you have actually tried this experiment, if you took any amplifier, in fact, any just circuit in general, and you fed it with a 0 input, You getting it? Or okay, there we go. Okay, so as we were mentioning, basically looks like it may just be low, so if you can go get some extra batteries, that. Okay, great, thank you. Okay, so basically the whole trick here is that because this is really coming about by essentially things being excited by just random variations either in temperature, or not in temperature, in kind of the motion of the atoms due to the fact that they have heat associated with them, it means that, again, you really cannot predict anything about what the actual value of a noise signal would be. The only thing you can say is something power you can actually collect. Okay. So just because those numbers tend to be useful, let's maybe sort of take a look at just some representative examples. Okay, so let's say that you, from whatever reason, were only interested in a 1 hertz bandwidth. So what it would tell you is that the maximum noise power you can, or the available noise power you can actually get out of some resistor is essentially 4 e minus 21 watts. Okay? So by the way, just because people like to quote this in dBm, which is just basically dB relative to 1 milliwatt, this is minus 174 dBm. Okay? Famous number. Keep it in mind. It's quite useful. Okay? So just to make sure sort of people are still awake and paying attention, if I, let's say, had a 1 megahertz bandwidth, what would my noise power be? Oh, okay, you did in dBm. Let's actually do it in absolute, because that's maybe hopefully more obvious for most people. The answer you gave was correct, but Yeah, exactly. It's going to be 4 e minus 15 watts, or 4 femtowatts. Okay? Now, by the way, one reason why it's actually really useful to keep these numbers in mind is that, there may come a day where somebody tells you, I want you to build a 10 gigahertz bandwidth amplifier with 4 femtowatts of input referred noise. So what's the problem? Say that again? Yeah, okay, you said you have to cool it, right? And you're basically correct because, and by the way, I should mention this is all at room temperature, right? It would basically say there's no way in heck you could actually do that without dramatically cooling the chip or whatever it is down versus the rest of the environment, okay? And by the way, there are some famous institutions which shall remain unnamed, which have indeed given design problems which broke all kinds of fundamental physics, okay? So, user beware. It's actually good to know these numbers because you can very quickly, do some calculations and come back and tell your instructor, no, this is ridiculous. What are you even trying to do here? Okay? Okay, so if we then actually try and sort of take this, right? So far I said everything about, well, okay, here's how much power you can get from sort of this thermal noise process. But usually we're circuit guys, right? We don't typically deal with power directly. We usually like to deal with voltages and currents. Okay, and we like to kind of come up with a model for predicting sort of the quote-unquote voltages and currents. So the way we're going to model noise in sort of our circuits is basically take our original noiseless element, in this case the resistor, and typically add some sort of either voltage or current source to that element to represent the noise signal. Okay? So in this case, I'm going to do it with the voltage version, but I'll show you in 1 second how you do this with current as well. Okay? So just before I go too much further, I did want to mention that even though I drew sort of a polarity on this voltage source, you should keep in mind I cannot predict the value of that voltage source. Okay? So all the analyses we're doing here are not to predict the value. It's only to predict essentially the variances. Okay? So in fact, oftentimes when I draw sort of a noise voltage, I won't even actually give it a value. Instead, I'll just draw sort of this squiggly symbol like this. Or in fact, excuse me, I won't even draw the polarity. I'll just give it a squiggly symbol like this to indicate that this is really a noise voltage. Okay? So in particular, you should be very careful that, for example, if you had two noise voltages in series, and you just so happen to draw them like this, if those are two independent noise sources, you had better not cancel them out. Okay? They actually add, and they add in variance. I'll show that in one more second. Okay? So just keep that in mind, because that's a very sort of classic mistake that gets most people when they first look at this. Okay? So if we now want to figure out what the actual sort of quote-unquote value I should plug into this, and by the way, when I say the value here, what I really again mean is I want to know how much variance can be coming from that voltage source. Okay? So if I want to figure that out, what I can actually do is sort of use this power property that I mentioned earlier. Right? I already said before that the power I can extract due to that thermal noise is just kB times T times the bandwidth. Okay? Well, so if we sort of think about this, if you guys remember, back in hopefully like the very first EE class you took, we always said that if you wanted to extract the maximum power from some source with a given resistance, you should always load it with that same resistance at the output. Okay? So what I'm going to do now is I'm adding this resistance externally, not because there's a real resistor that I want. It's just I'm going to use this resistor to figure out what is the actual variance of this voltage that would essentially tell me, or rather, I'll use this resistor to basically figure out what's the maximum power I can actually get, and therefore to calculate what the variance should actually be. Okay? So if indeed I took this resistor with a noisy voltage source and I loaded it with another resistor of the same value.
Wait, is the second resistor also considered noiseless?
So the question was, is the resistor considered noiseless or noisy? This second resistor we'll consider to be completely noiseless. Because again, it's just a fake resistor that I'm putting here to try and calculate what should the value of the voltage variance be, such that I get the power that I can actually extract from a thermal noise standpoint. Okay? So, if this was the case, then let's say that I knew what the variance of the voltage source was. How much power would I be dissipating in that resistor as a function of that variance? Or is it just even as a function of that voltage source? Let's say somehow magically we knew what it was. Okay, you said that if I told you what this voltage was, then the power that's dissipated there is V squared divided by R, right? Okay, so what is VR as a function of the noise voltage Vn? And I obviously didn't write the whole equation there, so don't assume that they're equal. Yeah, it's 1/2, right? You just have a resistive divider. Okay? So that means that the power that's dissipated on that fake resistor is essentially just Vn over 2 squared divided by R. Okay, which of course, if you do some very simple math, just tells you that it's Vn squared over 4R. Okay? So if you basically just take that and you say, well, look, we only put this resistor in the first place to figure out how much power you could actually extract from the resistor. You say, I'm now going to set that to the maximum power I could extract. You can quickly then calculate that the noise voltage variance is just 4 kTr times delta F. Okay? And the factor of 4 here, again, just came because of this voltage divider that we had. The R just comes about, obviously, because of the matching that we were doing. Okay? Is this clear to everybody? Or? Now, let me maybe ask you guys a question, sort of similar to what we discussed before. In this expression with noise voltage, what can you actually control? What's under your, degree of freedom to play around with? Say that again?
The bandwidth and the R.
Yeah, okay, so you said basically only the bandwidth and the R. Now, by the way, oftentimes the bandwidth is going to be specified by things that you can't control either, right? So there's, let's say, a certain speed of signal you're dealing with, or there's a certain, variation you're interested in. Oftentimes the bandwidth is just going to be spec'd, again, by the system you're trying to build in the first place. So basically it only comes down to this R, and then even actually there, oftentimes the resistor is going to be fixed by sort of other things that will come into the picture in terms of setting some characteristic of your circuit. So the point here is that oftentimes there's not really a lot you can do to really tweak this per se, other than maybe just, for example, spending more power. Okay? So the point to say there is not that you're sort of just stuck with noise. It's more to say that basically these noise calculations at the end of the day, they're typically fairly simple, only because there's really very little degrees of freedom you have in terms of basically figuring out what those values are. And so that's why it's kind of all the more important to really get this right, because basically if you don't, the noise is going to come out and just be larger than you wanted it to be. Okay? So here I'm just showing basically a kind of more complete picture of this, which is, remember I said before that I was deriving what the sort of voltage source would look like, but we also said we could equally model it with a current source. Indeed, you can sort of see that if I instead do the current source model, now rather than placing the source in series, I'm actually going to put it in parallel, right? And that's just sort of the simple standard Thevenin versus Norton kind of equivalent. And as perhaps is not too surprising, if you're modeling everything as a current source, remember, for the voltage source, the variance is proportional to the resistance. Now instead, the current variance is proportional to 1 over the resistance. So maybe just to say this in a slightly more clear way, it basically says that the noise current variance is actually proportional to the conductance. Okay? Which again maybe kind of makes sense because conductance and resistance are sort of inverse of each other, just like the sort of voltage in series versus current in parallel. Okay? Does this make sense to everybody? Or? Okay, now one thing that I should point out, because we're actually going to make use of it in 1 second, is that it turns out that thermal noise basically exists in all elements that dissipate power. Okay? But in fact, you can actually make an even stronger statement than that, which is thermal noise can only exist in elements that dissipate power. Okay? So for those of you guys who like physics, this is the so-called fluctuation dissipation theorem. Keep this in mind, because we're going to actually use that in 1 second to sort of give you a little bit of a brain teaser and see if you guys can figure out what's going to go on there. Okay? Another important point to keep in mind is that the thermal noise that you get is totally independent of how much DC current you're flowing through the resistor. So if you flow an amp versus a milliamp versus a microamp, thermal noise is exactly the same as long as the temperature of the resistor is the same. Obviously, if you melt the resistor, then other things will happen, but as long as the temperature doesn't change, thermal noise is totally independent of the DC current. Okay? So as we've mentioned a couple times, but I'll just reiterate to make sure it's absolutely clear to everybody, right? Remember, when I'm drawing these circuit elements here, you should not treat them as a deterministic voltage or current source. You should remember this is really modeling a random process. Okay? So even though even though you've drawn these elements kind of the same way we would draw the other elements, and in fact you'll do many of the analyses in a very similar way, you really have to keep it in mind that this is random sources. Okay? And we'll say some more about that in 1 second. As we said before, the mean of these noise sources is basically always 0, because if it wasn't, then something very weird is going on. It turns out that in almost all cases, the so-called distribution or probability density function is Gaussian. And again, just the only thing I mean by that is that essentially, if I draw a plot of the probability of getting a certain value of the voltage, of the noise voltage, versus, of course, the noise voltage, you'll see some distribution that looks Gaussian. And, my Gaussian doesn't look particularly good. It probably is skewed and stuff like that. But, just pretend I drew a good-looking Gaussian there. That's indeed what the thing should look like. Okay? The other thing that is kind of interesting to note about thermal noise, particularly in the context of just a resistor here, is that the so-called power spectral density is white. Okay? So what I mean by that is the following. If I do a plot of essentially, let's think of it as kind of the magnitude of the voltage noise as a function of frequency, then basically thermal noise is really flat. Okay, in other words, it's the same at all frequencies. Now, there's some minor caveats there of, if you really get to ridiculously high frequencies, this is no longer true. Don't worry about that for now. Okay? So when people say that noise is white, what they actually mean is that it's equally distributed over all frequency bands. Okay? Now, just to be totally clear, in the time domain, what does that mean? Like, what's the sort of interpretation of that? Does anybody know? Okay, you said it's a delta function. Let's see. That's in some context that's correct, but what do you mean? There we go. That's exactly what you mean. So basically, if you have something that's completely flat over frequency, it means that any two samples of the noise in time are completely uncorrelated. In other words, if you were to just go and measure noise, at one time, and then measure it, let's say 10 picoseconds later, there'd be absolutely no correlation between those values. In other words, knowing the value 10 picoseconds ago would tell you absolutely nothing about the value now. Okay? That's really what sort of this white noise means in the time domain. Okay? So again, just to sort of give you some examples in terms of real numbers, because these are sort of useful to make sure that everything's understood. If I had a 1 kilo ohm resistor, then basically the noise density coming from that resistor would be 4 nanovolts per root hertz. Okay, now this unit sounds a little bit weird, but remember, we've said a couple times now already that it's actually the variance that's proportional to both the resistance and the bandwidth. So here I just quoted everything in terms of voltage. So if I'm quoting in terms of voltage, that means that you're proportional to square root of frequency, not to the frequency. Okay, so again, just keep in mind the difference between variance and standard deviation, because it's a very sort of common thing to get messed up on, especially when you first play around with these things. Okay? Of course, once you specified the bandwidth, in this case, let's say it was 1 megahertz bandwidth, you would get, for example, 4 microvolts of standard deviation of noise from a 1 kilo ohm resistor. Okay? And again, you should remember, when I quote this, it's not that I'm saying the value is 4 microvolts. I'm only saying the standard deviation is 4 microvolts. Okay? There is still a finite, but there's still a finite and non-zero probability that even with only 4 microvolts of standard deviation, that you have a volt of noise out of the resistor. Okay? It's extremely unlikely, obviously, but it can, in theory, happen. Okay? Does this make sense to everybody? Or? So now, let me maybe sort of give you guys a little bit of a brain teaser. Okay? So let's say I just go and I take some physical capacitor. Okay? My question to you guys is, does that capacitor generate any thermal noise? And let's maybe take a vote just to, get people moving a little bit. So who thinks that capacitor will have thermal noise? Okay. Well, you asked a very interesting question. We'll come back to that. So 3 people said that it will. Okay, who says it will not have thermal noise? Okay, many more people. So that's good. So now, you actually asked a very interesting question. So you said, is it a real capacitor or is it an ideal capacitor? So what's the difference? Why would that matter if it's real or ideal? Okay, so you said a real capacitor also has resistance. So why does that matter? Why would that change the question, or the answer, I should say? Yeah, okay, so what you basically said was that if my capacitor had some parasitic resistance in it, that parasitic resistance indeed could generate some thermal noise. Okay? But if it was really just an ideal capacitor, as I said a second ago, an ideal capacitor cannot have thermal noise in it. Okay? Or cannot generate thermal noise is really the more accurate way of stating it. Now, it turns out the reason for this is actually kind of interesting. As I said, there's a whole bunch of statistical mechanics and other weird physics you can get into. But there's actually kind of a nice circuit way of seeing why that has to be the case. Okay? So the way to see that is fairly straightforward. So if we're in so-called thermal equilibrium, meaning that the temperature of all of our components is the same, right, then we can basically sort of make a simple statement, which is that any power that's dissipated by one element due to thermal noise had better be the same as what's delivered by the other element, and vice versa, right? Because if they're not, then obviously one is transferring power to the other and heating it up, right? So in particular, let's do a very simple thought experiment, okay? So let's say we take a resistor and we put it in parallel with a capacitor, okay? So in this particular case, again, if we're in thermal equilibrium, it had better be the case that the power we dissipate in the resistor is essentially equal to the power delivered by the capacitor, okay? And again, vice versa. It had better be the case that the power dissipated by the capacitor is equal to the power delivered by the resistor, okay? So now, let's do sort of a simple thought experiment. Let's say that indeed the capacitor has some noise voltage associated with it, okay? So in this situation, what would happen? What would how would that noise voltage or the noise energy really basically kind of, what would happen to it? What would dissipate it and what would not? And remember, in this particular case, we're modeling the thermal noise as actually coming from the capacitor. So would the resistor dissipate that energy or not? What do you guys think? If I put voltage across the resistor, does it dissipate energy or not? Yeah, it does, right? The resistor would perfectly happily take whatever energy is coming out of the capacitor and dissipate it, right? So in other words, basically saying that voltage noise appears on the resistor, and the resistor dissipates that energy, right? Okay, well, so does this bother anybody? Is there kind of a problem with this? Is it totally okay for just, a resistor to be dissipating energy that came from apparently nowhere? What do you guys think?
No, because if that were the case, then you have like a thermal energy source.
Yeah, exactly, right? You're somehow magically getting energy out of the capacitor without it being coming from anywhere else in the world, right? That's obviously bad, right? So just to be clear why the flip is actually okay, right? So what this basically says is that this is bad, right? This can't possibly happen because we just have sort of energy kind of coming out of nowhere and somehow magically we're heating up the world, which, again, basic physics says you can't do, right? So just to be sort of clear as to why this is different than the resistor actually generating it. So notice, if my resistor is actually what's generating that thermal energy, right? The capacitor doesn't really actually do anything to that energy, right? All it does is it stores it as electrical energy, and then eventually as the sort of, as the, let's say, voltage across the resistor changes, the resistor will then redissipate that energy, right? So in other words, there's no net energy transfer one way or the other, right? The resistor is generating something, but at the same time, it's going to eventually dissipate the exact same energy, okay? So that's why in some senses, this is sort of okay, but this is not, right? And again, the trick there is just that because the resistor can also dissipate energy, it's totally fine for it to have a thermal noise generator, right? Because it can also dissipate whatever it generated in the first place. Whereas a capacitor has no dissipation mechanism, and so therefore can also not be generating any thermal noise. Does that make sense to everybody? Or? Okay, so just to make sure sort of a lot of this stuff is really totally clear, I want to sort of just walk through a few examples to make sure everybody's kind of really got this. And the rules that we're going to be following are actually sort of highlighted up at the top over there. But rather than maybe me walking through the rules, I'll actually sort of make sure that they're clear by asking you guys a few questions. Okay? So first, as we were kind of hinting at a little bit before, let's just do a simple example where I tell you that there's two independent noise sources. Let's call it V1 and V2. Okay? And I want to know the total noise at the output. So you guys tell me, what is the total noise at the output as a function of those two sources that I've drawn there?
Summation.
So when you said summation, which is absolutely correct, but summation of what?
Power.
Summation of power, exactly. So you have to be very careful here, right? So you could not say that VON is equal to V1 plus V2. The only thing you can say is that VON squared is equal to V1n squared plus V2n squared. Okay? In other words, again, you have to be very careful about adding powers or variances and not voltages. Okay? Now, obviously, if you were to look at in time, indeed, the instantaneous voltage at the output would be the sum of V1 and V2, right? But that does not mean that the variances are what that would imply, right? The variances always, you add in variance, not in standard deviation, okay? And this is true as long as those two voltage sources are independent, okay? Or those two noise sources, I should say, are independent. Okay, so similarly, let's take kind of another example. Let's say I had kind of two resistors in series. Okay? So let's say R1 and R2 here, right? Okay, so what would be the noise voltage due to R1? What is that? Yeah, it's just going to be 4 kT R1 delta F, right? Okay, similarly, what's the noise voltage due to R2? Okay, somebody's whispering it. Just speak up. Yeah, exactly. 4 kT R2 delta F. Okay, so now I should be able to take this and simply model it as R1 plus R2, right? And if I've modeled it as R1 plus R2, then the noise voltage from that should be equal to 4 kT R1 plus R2 times delta F. Okay? So, notice here that, again, the only way that this would have worked, the only way it would have been self-consistent, is indeed by making sure that when we added these two voltages in series, we actually added them in variance, right? Because if you added these in voltage, right, you wouldn't have gotten this back, right? You wouldn't have gotten this equivalence, which intuitively should have actually held, right? You should always be able to take a resistor that's some total value and split it into two pieces and be able to get the exact same answer out, right? So again, this is just another sort of warning. Make sure you're very, very careful about adding variances and not in standard deviations, because you'll get all kinds of things that are just completely messed up if you try and do it that way. Does this make sense to everybody? Or? Okay, great. So we'll finish up with this on Tuesday, so I'll see you guys all then.